So 14.6. So the first thing we're going to do is develop the idea of a triple integral. It's very similar to what we've done for double integrals, using the same kind of procedure. So for the way that we're going to set it up is we're going to say that our function is some function of x, y, and z, and it's continuous on some solid region Q. And we're just using Q just to help us remember that we're talking about a solid rather than a planar region. So to set this up, here are our axes, and we have some solid so there's a solid in the first octant. And the solid is given by our function f of x, y, z. And we're going to divide this into small rectangular prisms. So inside here, let me draw my prism a little better. We're putting the sides of the prism parallel to our coordinate axes. So that's a little piece inside, a little rectangular prism inside our solid. And we're going to call the volume of that delta v sub I. And the sides of our rectangular prism are going to be delta y sub I, delta x sub I, and delta z sub I. So we have this tiny little rectangular prism. I guess initially it doesn't have to be tiny, but eventually we'll make it tiny. So delta v sub I is just all of our delta x, y, and z multiplied together. And x sub I, y sub I, z sub I is just the point at a point in the box. So to find the volume, what we're going to do is we're going to form the sum of the sum I equals 1 to n of our function times our delta v. So we can, and we'll interpret this function in different ways. We could think of it as the density function. So we have a density defined at a point in space, and we're going to sum the density times the volume to get the mass of the region, for example. And then we're going to take this sum, and we're going to take the limit as delta v sub I approaches 0, just like we did with double integrals with our delta a approaching 0. Same idea that we're taking the limit as the smallest diagonal approaches 0. So we're saying delta v sub I approaches 0. And so this leads us to our definition of the triple integral. So we're going to say the triple integral of over Q of our function x, y, z dv is this limit, and I'm saying delta v approaches 0. I'm being loose with the terminology there. And we're just taking the limit as the sum of this sum. So this is our definition of a triple integral. Exactly analogous to how we defined a double integral. So this should be familiar, somewhat familiar now after we've done double integrals. And if we just are interested in the volume of this region, the volume is going to be just a triple integral of dv. Triple integral q of dv. So just like we could take the double integral of dA to get the area of our region, we can make a triple integral of dv to get the volume of our solid region. So triple integrals are going to have a lot of the same properties as single integrals, and as double integrals we can add them, we can multiply them by a constant, etc. I'm not going to list out all of those properties, but if you can review them on page 1024. So properties of triple integrals. But they're all those familiar properties that we use for single integrals. If we have a simple region that we can divide into rectangular prisms easily, we evaluate triple integrals like we did double integrals. So our dv element is going to be dx, dy, dz, or some permutation of those three quantities. So we end up with 6 possibilities for orders of integration. Usually when you're doing triple integrals in rectangular coordinates, you're going to represent dv as dz, dx, dy, or dz, dy, dx. Usually the z is going to come first. So I'm just going to write out one example of how we evaluate triple integrals, one list, and just realize that we can permute the dx, dy, and dz in 6 different ways. So if we have, if a is less than or equal to x, less than or equal to b, and h1 we have some function of x is less than or equal to y, less than or equal to some other function of x, and we have some function of x and y is less than or equal to z, less than or equal to some other function of x and y. So these are our boundaries, our limits for our integrals. Then our triple integral over our region Q is just going to be the integral x equals, and with triple integrals it can be helpful to write your variable in so you remember. So x equals a to b. You don't have to, but it can help you remember. Y equals h1 of x to h2 of x, and the integral z equals g1 of xy, g2 of xy of our function, and this order is going to be dz, dy, dx. And we evaluate triple integrals just like we did double integrals, where if we're integrating with respect to z, we hold x and y constant, etc. And depending on how we set up our region, we could have 6 different permutations of dz, dy, dx, and we would have the different limits that go along with those. But again, usually you're going to set up triple integrals in rectangular coordinates as dz dy dx or dz dx dy. You don't have to, but usually that's the way you do it. So questions on our setup here. All right, let me see where we are. Let's do one or two quick examples with triple integrals, and then we'll talk about applications. So, we want to, in this example, we want to find the volume of our region and our region is bounded by these functions. Z equals 9 minus x squared. Z equals 0, x equals 0, and y equals 2x. So when we're setting these up, it can be helpful, just like with double integrals, to sketch our region. So let's do a quick sketch of what we're talking about here. So z equals 9 minus x squared. What kind of surface is that? A parabola, and downward facing parabola. And what does it, so we end up with something like this in the YZ plane. And so what makes it a surface?
It can go anywhere along the other axis.
Go anywhere along the other axis. So I said YZ plane, I meant XZ plane. So it goes anywhere along. So we have this kind of parabola shaped it's a parabolic cylinder. So it goes along the y-axis there. We're bounded by z equals 0, x equals 0, and y equals 2x. So where is y equals 2x?
XY plane.
XY plane. We just get a line in the XY plane. As a surface, this would be what? A plane. So we have this plane cutting through our surface, so our surface is going to be cut along that plane. So we're cutting a wedge out of that parabolic cylinder with the plane y equals 2x. So in the XZ plane, we have this parabola. This is 9 minus x squared. This is x, and this is z, and this is x equals 3. And in the xy plane, we have y equals 2x, and we go to, this is x equals 3 over here. So we're in this region in the xy plane. So our volume, the volume of this surface is going to be given by the integral x equals 0 to 3. The volume, or the integral y equals 0 to 2x. And the integral z equals 0 to 9 minus x squared. dz, dy, dx. So I integrate up to our surface first, then I integrate to our limits here, and then I integrate along the x direction. So that integral would give us our volume. Questions on how we set that up? All right, let's look at an example going the other direction. So let's say we have the triple integral 0 to 4, the integral 0 to 4 minus x over 2, and the integral 0 to 12 minus 3x minus 6y over 4 of dz, dy, dx. And we want to sketch the region. So we have this triple integral. We want to sketch the region. So let's go outside in. From the limits, what does it tell us about x? 0 is less than or equal to x, less than or equal to 4. And y? 0 is less than or equal to y, less than or equal to 4 minus x over 2. And for z, finally, 0 is less than or equal to z, less than or equal to 12 minus 3x minus 6y over 4. So let's look at the z. If we can sketch this surface, what is this surface? A plane. So let's sketch the plane. Z equals 12 minus 3x minus 6y. So I can rewrite this surface, z equals 12 minus 3x minus 6y over 4. I get 3x plus 6y plus 4z. Do I have a minus sign there? Yeah, that's right. Plus 4z equals 12. So I'm just taking z equals 12 minus 3x minus 6y over 4 and rearranging it. So how can I sketch that plane? Intercepts. So when x and y are 0, z equals 3. So I have a point here at z equals 3. When y and z are 0, x equals 4. And when x and z are equal, y equals 2. So then I connect those and I get where my plane cuts through that first octave. And this line is y equals 2 minus 1/2 x. So there's my region. Now what if it asks us to rewrite our integral in order dy, dx, dz? So rather than going up to our surface, we're going from the y-axis, going over to our surface from the yz plane. So we need to write this plane as an equation y equals some function of x and z. So we would rewrite that y equals, or we'd say y equals 12 minus 3x minus 6z over 6. So I'm just getting this as a function of y. 4z? Yeah, 4z.
Why are you rewriting it in
We want to change the order to dy, dx, dz. So for my, So y has to be first, so we're thinking of the surface as a function of y. And then we need x as a function of z. So in the xz plane, we want the equation of this line. So we have x equals 12 minus 4z over 3. And finally y, or z, is just going to vary from 0 to 3. So we can rewrite our integral z equals 0 to 3, x equals 0 to 12 minus 4z over 3, and y equals 0 to 12 minus 3x minus 4z over 6, dy, dx, dz. So changing the order of integration in triple integrals is a little more involved. So it's nice to be able to pick and set it up in a way that works nicely. But we do it the same way. We just examine our region, figure out our limits for the particular order that we're interested in. All right, questions on that example? Now, with triple integrals, depending on your shape, you may have to, after your first evaluation, if you evaluate dz, if your surface is nice, evaluate dz. Sometimes it's easier to switch to polar coordinates to evaluate the other two integrals in the x, y, your x and your y integrals. So you may evaluate one integral in rectangular coordinates, another integral in another two integrals in polar coordinates, or you might switch to polar coordinates from the beginning. So with triple integrals, you have a lot more choices as to how you set up and evaluate your integrals, because you have that extra variable that you're working with. All right, questions before we move on? So a couple of applications of triple integrals. Because now we're dealing with solids, we can talk about centers of mass and moments of inertia of solids. So rather than a planar lamina, we can talk about these ideas with solids. So for these applications, we're saying that rho, our density function, is a function of x, y, and z, and this is our mass per unit volume. When we talked about planar lamina, we said rho was mass per unit area. So we have mass per unit volume, and using triple integrals now, our mass of some solid is just a triple integral over our region of rho dV. Our first moments. And remember, first moment just means we're weighting our quantity by its distance from an axis. And the first comes from the first power. So our first moments, we have several first moments now. The moment m sub yz is the moment about the yz plane. is a triple integral over our region of x rho dv. X is the distance of our little increment of mass from the yz plane. And then the other two moments are just the different combinations of our variables. So m sub xz is a triple integral over a region of y rho dv. And our third one that we have here, which combination don't we have? Y, xy. Triple integral of z rho dv. So we're just multiplying the little increment of mass times its distance from a particular coordinate plane. And our center of mass is just, we're going to have three coordinates now. Each of these divided by the mass. So our center of mass our x bar is m sub yz over m. Y bar is m sub xz over m. And z bar is m sub xy over m. So that would be our center of mass of our solid. So we're setting these up, again, much like we did with double integrals. We also can talk about our second moments, or our moments of inertia. And we can talk about lots of different moments of inertia. So we said moments of inertia that measures the kind of the resistance of an object to rotate. So now we have a solid. We can talk about this moment of inertia about various axes. So I'm just going to list out our second moments. Very similar idea. And our second moments are, we also call them moments of inertia. So I sub x is our moment of inertia about the x-axis. So we need our distance from the x-axis when we have a point in space. So this is our second moment, or our moment of inertia about the x-axis. The others are just the different combinations of our variables. Triple integral so this one's about the y-axis. Same thing for our second moment about the z-axis. So there's our three moments about the coordinate axes. We can also talk about the moment of inertia about a plane. So I will, if everybody's got these, I'll switch to the next page. Everybody good here? So we can talk about our second moments about the coordinate planes. So I sub xy is a triple integral over our region of z squared rho dv. And this is about the xy plane. And then the others are just the different combinations of our variables.
Are these still the moments?
These are still moments, yes, second moments. So I sub yz is going to be the integral of x squared rho dv. And I sub xz is going to be the triple integral of y squared rho dv. And the reason that we're talking about these moments about the planes is we can say, now let me go back here really quickly. I sub x involves y squared plus z squared rho dv. And depending on your density function, this triple integral can be difficult to evaluate, where these integrals just involve a z squared, an x squared, a y squared. So the relationship between these is I sub x is I sub xy plus I sub xz. I sub y is I sub yz plus I sub xy. And I sub z is I sub xy plus I sub yz. And using these can save a lot of effort. I x, yes. So using these to calculate can save you some effort. So if you calculate these three and then form your sums, it can be easier than calculating these directly. So questions on all of these setups? All right, let's see. Let me do one example here of finding a centroid, and then I will post up a video doing a couple of other examples. I just want to do this one because because I want you to see this particular setup. All right, so we're going to start with our region. Sketched. And we might not be able to go through the entire example, but I want to talk about the process here. So this point is 0, 0, 4. This point is 5, 0, 0. And this point is 0, 3, 0. And our problem here is we want to find the center of mass. of this region, we're assuming that rho equals some constant, or I'll say rho equals a k rather than 1. So what are we going to have to do here to find our center of mass? All we have are points. What do we need to find our center of mass? We need triple integrals. For triple integrals, we need limits of integration that are functions. So what's our first limit of integration needs to be, if we're thinking of a surface, we need the equation of this surface. And then we need equations of the boundaries in the coordinate planes, so we can set up our limits of integration. So we need an equation of our surface. How are we going to get an equation of our surface? What kind of surface is it? It's a plane. So how are we going to get an equation of this plane? Anybody have an idea?
Well, for one thing, when x and y are 0, b equals 4, so
Okay. We have a point on the plane. Well, so think back. What do we need to write the equation of a plane? Direction numbers, which come from a normal vector. So we need a normal vector. We need a normal vector to our plane. How are we going to find a normal vector to this plane? Let me give you a hint. What if I drew a little arrow here and a little arrow here and said those are vectors? Take the cross product. So we can form vectors out of two sides from these points and take the cross product. So we get a normal vector from the cross product of the vector between two of these points. So the normal vector from the cross product. Once we find the normal vector, then we can use Mehmet's suggestion. We have a point on the plane. We know 3 points that are on the plane. So then we can write our equation for our plane. Once we get our normal vector from our cross product, we can write the equation of the plane. Then we can rearrange that and say z equals something. So we'll get an equation for the plane. From the lines that it makes in the coordinate planes, we would get y equals some function of x in the xy plane. So we get our limits of integration on y, and then we know that x varies from 0 to 5. So we could set up our triple integral to find our center of mass from those pieces of information. So what I'm going to do is I'm going to stop there because we're not out of time, but I don't want to go clear to the end. I will finish this example in a separate video, and I'll do a couple of other examples with triple integrals in a separate video. All right.
So, do we all produce like surface area integrals?
No, surface area will be double.
You get all the other questions like at the same time you do double. So I was wondering.
No, we'll do some other things with triple integrals.
So I don't understand like why what we have 3D surfaces with triple integrals and double integrals. So I like
it's so what we're going to do is